but I'll get back to it later on. So let's talk about how we analyze the function for maximum minimum. In other words, how we implement the second derivative test. So here it comes. So we're going to say that suppose the point AB is a critical point of a function f of x, y. And that the second derivative, the second order partial derivative, remember that will be f sub xx, f sub yy, and f sub xy are continuous. In some region containing AB. So this is the position. Then here is the definition, define. And this is where we're going to define. We're going to write it as a determinant of the second order partial derivative. So, and we'll give it the letter D. D will be, in this case, it will be D of AB, like so. It is the determinant of this. You remember the second order will be, we have f of xx, or f xy, f yx, and f let me write it differently. If this is x row and this is column, so it will be fyx here. I did it right in the first place. It makes no difference because we're talking about the cases, in our case, f of xy and f of yx are all the same. But what is this? If you do the determinant of a 2 by 2 matrix, you have f of sub xx times f sub yy. Let me write it here. Minus f of xy times f sub xy times f sub yx. Well, if they equal each other, I can write it as f sub xy squared, like so. Okay? And this is how we defined D. And why is it important? Because now we have the following classification. So then we have the following outcomes of classifications. So 1, okay, we're going to say that if D, the determinant, is positive and the second order derivative f sub xx is also positive at AB, then what do I think you will have? What was the case when you have f prime, when you have a critical point, the second derivative was positive in Calc 1, in single variable? We had a relative minimum, right? So it's here. If D is positive and F YY is of AB is negative, let me stop here before I move on. Let's stay with condition 1, okay? I didn't tell you what is the sign of FYY, but can you tell me? You should be able to tell me what is the sign of FYY. There's only one possibility. It has to be positive, because look at the determinant. You have something times something minus fxy squared. Well, fxy squared, regardless whether fxy is positive or negative, it's always positive. So we are subtracting something. So for this to be positive, for D to be positive, if fxx is positive, so is fyy. If fxx is negative, so is fyy. fxx and fyy have to be of the same sign in order for D to be positive. Okay? So I could have switched, I could have swapped fxx with fyy and have the same thing. So what is the distinction? The distinction is this one. If fyy is negative, so is fxx. But what is the difference? The difference is we, instead of having a relative minimum, we'll have a relative maximum. All right, third condition. What happens if the determinant, or if D is negative? Okay, then the point AB, can you guess what it is? Is, you wouldn't know that because you were not here at the beginning, but let's go back. This is what happened. Again, on the, those of you who were late, on the Z, Y, we have relative, we have a minimum. On the Z, X, we have maximum, okay? And if you look at it like so, you can clearly see a shape of a saddle. So that's a saddle point. And what it does, because on the ZX you have a maximum, and on the ZY you have a minimum, you have FXX and FYY have opposite sign. So the determinant is negative. The product fxx times fyy is negative, and you have, of course, minus the square of the gross second order derivative fxy. So the determinant is negative, and that's why you see a saddle point in this case. Okay? Go ahead, James.
Is that form forever? Is that just like where it is? I mean, like if you were to open that box, it's going up.
It depends on the function. In this case, if you continue this way, but it's not necessarily always the case, because we may have polynomials, mixed polynomials, so you'll have peaks and valleys, depends on the direction you go. So that's why we said relative or local extrema, relative maximum, relative minimum. But the point is, as you can see, we're both at the same point with maximum minimum. Depends how you look at it, or what's the cross section. That's why it's a saddle. It's neither relative, neither maximum nor minimum. All right? Right there. Right? You see it very well here. This is the point in on the x, y, z, and the x, z plane. So you have some x sub 0, y, z sub 0, right? So this will be, let's call it AC. And then you look here at the x, z plane. I'm sorry, you call it, this is the y, z plane. So now you look at this point, this will be y equal b, z is still going to be equal to c. So, and now if you look at it in 3D, then that point right there will be the point A, B, C. X equal A, B equal Y, Y equal B, and Z equals C. All right? Going back to the paper then, we'll take it from here. So we have a saddle point when we have the determinant is zero, is a negative. And the last condition, if the determinant equals 0, then we don't know. We need to do something else. So it can be a relative maximum, relative minimum, or saddle point. We just need to do something else. Other techniques are required. All right, so now we can go back to the previous example and finish the analysis of to determine whether we have and perhaps even see that we have other points on this function, because really we didn't discover all the points in this case. Okay, so I'm thinking, could we obtain other points from this deal? Let's go to the previous example. Where was it? Have we missed something here? I think we have. Oh, I'm looking at a different example. I'm so sorry. I was looking at the wrong example. No, we are good to continue. So let's continue. Continue our previous example. Okay, we have the distance d squared f of x y was d squared, was the function, let's write it, x plus 2 squared plus y plus 1 squared plus negative 4 minus 4x plus 2y squared, right? And we want to find minimum f of xy, and the critical point was xy was equal, let's see, what we come up with, negative 34 over 21 and negative 25 over 21. Okay? And now we want to analyze whether it's a minimum or maximum. So what we're going to do, we're going to need to have three more derivatives, right? We need to find f of xx, fxx, the second order derivative. So let's look back at what we have. We need to write first fx, the first order derivative. I had it, and it was 34x minus 16y plus 36, and f sub y was negative 16x plus 10y minus 14. So now we need fxx. Well, the second derivative of x with respect to x would be 34, and that's it, isn't it? Okay. What about fyy? Well, the second derivative of y with respect to y it's simply 10. What about the mix, f of xy? Well, we can take this derivative derived with respect to y, right? So it would be, remember, it's del del y of fx, like so. So it would be negative 16, right? And they should be equal to fyx. If you take this, and you can see that it should equals to f of yx. We talked about the del del x of fy, like so, and you take the derivative of fy with respect to x, and you get negative 16. So we have these three numbers, and now we can find d. All right, so what is d? Well, d, the discriminant, equal fxx times fyy minus the square of xy, fxy, like so. So we have 34 times 10 minus negative 16 squared. So we have 340 and minus 256. So it's positive. We don't care what it's equal to as long as it's positive. All right, so what's the conclusion? We have a positive determinant, and fyy is negative, isn't it? So we have condition 2. I'm sorry? fyy is positive. So we have condition 1. No. fyy, condition 1 was fxx greater than 0, fyy greater than 0. That's what I meant, that it's the same thing. So we have condition 1. Okay, so d is greater than 0, and if both fxx and fyy condition 1. Therefore, we have condition 1 gives us relative minimum. Negative 34.21, negative 25.21. So what's the conclusion? that's the point where the distance between the point, the original point, what was that one, forgot where we started. -2, -1, -5 is the minimum. Okay, so therefore the distance from the plane (4x minus 2y plus z) equals 1 to the point -2, -1, and 5 is minimal. Is minimum at xy equals -34 over 21, -25 over 21. Okay. What are we missing in this? What about z? I mean, we have x, y, and z. So we need also to include z in that one. So, however, let's not forget z. That's how we replace z with 1 minus 4x plus 2y. You recall that? So it's equal to 1 minus 4 times -34 over 21. So you have a little bit of arithmetic before we can conclude this. So, and this equals to let's see, that is correct. Let's see, you have 21 plus 136, right? And here we have minus 50 over 21, so and that will be 150. Oh, 157. Okay, 107. Get a little bit. So the closest point to -2, -1, and 5 is the point, and now we are done. The point -34 over 21, -25 over 21, and 107 over 21. All right. I think this is a good time to stop, isn't it? What I need to do to complete this section is talk about